Alright, so let's talk about chapter 16, which will be on climate change. Alright, so historically, let's start off historically by showing you what has been documented about climate change in the past. And in Earth's history, there have been periods of warmer climate and cooler climate compared to today's climate. So today, I would say it's pretty warm, but there have been times in Earth's past where it has actually been warmer than it is today, and there have been times where it's been colder. Usually the colder periods are associated with ice ages, and climate change in the past has primarily been dominated by natural processes. So we will talk about what these natural processes are in a little bit, in a few more slides. But currently, our climate change that we're experiencing right now is primarily due to human activities, and we'll see why that is in a little bit. So you can see some of the images in this slide here. On the left-hand side, there's drought. So some places are experiencing more drought than usual, so less rain. You can see on the right-hand side there's an image of deforestation occurring, where they're burning down the trees in the forest to make room for grassland so that they can feed the cattle. And the middle image right there is showing you industrial power plants that are releasing gases into the atmosphere. So we'll talk about all of that in this lecture. So before we continue on with current climate change, we have to really understand why climate change is such a problem and why it's even happening in the first place. And the reason why climate change is the way it is because our climate system is made up of 5 different parts, and they all interact with each other, and they all influence each other to some varying degrees. So the 5 different parts of our climate system is the atmosphere, which is the air that we breathe, the hydrosphere, which is the ocean. Hydro just means water. The lithosphere, so the earth, so anything soil or terrestrial related. The biosphere, which is the animals and the organisms that live within the earth, and so bio means life, right? And then the cryosphere. The cryosphere is the glaciers and the ice at our polar caps. So you wouldn't think that has any impact, but you'll see why the glaciers and the ice caps are part of the equation in a little bit. But exchanges of energy and water between all 5 of these parts occur on a regular basis, and depending on whether you have more or less energy or water transferring between each part will determine whether we have a warmer period or a cooler period or just a normal warm period. But yeah, so whatever changes are made in the atmosphere will likely affect the other 4 parts. So let's look at this graphically. Here you can see the ocean. The ocean would be your hydrosphere. Then in the atmosphere, where you have your clouds and your rain, there's interaction between that. Then up on the mountains, you have your cryosphere, where you have ice and glaciers. And then your biosphere is typically on land, although you do have a biosphere in the ocean. And then you have your lithosphere, which is your earth. And so all of them are interconnected one way or another. Okay. So let's look at how, in particular, the atmosphere is connected to the ocean. And one way that you can see that they're connected is by looking at the feedback loops. Now, feedback loops are processes that change the initial conditions And when you change the initial conditions, you can either have a positive feedback or negative feedback. And in this image right here, it's showing you the positive feedback that's occurring over the ocean. And then over land, you'll have a negative feedback that occurs above the cloud, but then you'll have a positive feedback that occurs below the cloud. So what's going on here? So essentially, you have heating that occurs on the Earth's surface, and when that heating occurs over the water, it causes the water to heat up, turn into water vapor, and go into the atmosphere. And when that happens, the water vapor traps in the heat that would otherwise escape into space, and you create a warming effect. So your initial condition will be warming, right? Because you're warming up the surface of the water and you're creating water vapor, and your end result will enhance the initial condition. So you continue to warm in a positive feedback situation. Whereas in a negative feedback situation, your initial condition is warming, but then that water vapor condenses and turns into clouds, and those clouds then block any further sunlight from reaching the Earth's surface. So in that sense, you have a negative feedback. So there's a cooling effect in that sense. Um, you do have a slight positive feedback underneath the cloud because it does trap heat, but the overall effect is a cooling because you don't have that additional sunlight coming down and heating up the Earth's surface. So let's go back to climate change. Now that you understand a little bit more about the climate system and how they're interconnected, but I pose this question to you: what is real? Because when you go and do a Google search of climate change and global warming, you get probably a gajillion articles. Some of them say, yes, global warming is a thing, global warming is happening, while you have others who say, no, global warming is just something that the scientists made up. It's a political move, blah, 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 so forth and so forth. All right. But how do you know which article is true and which one's not? In this comic here, it illustrates over time throughout history different theories that have come about and the type of arguments that people would say about that particular theory. So in the 15th century, you have people who are saying the Earth is round, right? Because they're looking at they're looking at astronomy and they're looking at what's going on, and they're fairly certain that the Earth is round. But then you have those other people who are naysayers, right? And they believe that the Earth is flat because that was the prevalent theory at the time. So the theory that the Earth was round was a new theory back in the 15th century and was highly regarded as hearsay and like speculation, and really people who were trying to convince the population that the Earth was round were crazy, or at least that's what they were led to believe. But in reality, we know the Earth is round, or at least my opinion is that the Earth is round. Not quite sure what your opinion is. But if we continue on into the 17th century, you can see, not Einstein, what is his name? Newton. Is it Newton? I think it's Newton. But anyways, the scientist who says, is gravity real? Explain this, right? And so you see a bird flying, right? So theoretically, if we didn't have gravity, how is the bird flying? So again, you see that there's always two sides to an argument. You know, there's one side that's like, no, I'm pretty sure this is a thing. But then there's another side that's like, well, no, there's no way this can be a thing because X, Y, and Z. So over time, you can see it has happened time and time and again. And even in the 19th century, where you have evolution, right? But then you have people saying, well, what about the Bible? Blah, blah, blah. Until you get to the 21st century, which is now, and you say, well, how is global warming real if we still have snow? So the main point of what I want to get on this slide is, while there's always going to be two sides of an argument, one that says, yes, this is a thing, and the other that's going to say, no, this is not a thing. Throughout this lecture, I want you to look at the facts and make your own decision. Don't just take my word for it and say, well, Professor Nathan said that global warming is a thing, so it must be a thing. Or if you read in the news nowadays and Trump says, no, climate change is not a thing, it's just made up, blah, blah, blah. Well, try to figure out and do a little bit of research why they're saying that. Because who knows, maybe your opinion will change on the matter. But in this lecture here, I'm not trying to convince you of climate change. I'm just trying to give you the facts and how it relates to the ocean. So you can make your own opinions, all right? So how have we determined the climate in the past? And what we have done, since we weren't there to take data, is we've done what's known as proxy data sources. Proxy data just means that we have taken our information from a secondary source. So while we don't have instruments in the past to tell us what the climate was like, we can look at such things like tree rings, for instance, to tell us what the climate could have been. Now, this is not an exact data source, so it's not going to tell us, oh, well, you know, in 89 AD it was 79 degrees average temperature. No, it's not going to be that. What it is going to tell us is whether there were periods of dry times or whether there were periods of wet times, or cooler or warmer times, just depending on what the information is. So let's go back to that tree ring example. If you see the image on the right hand side there in the middle, you can see in the middle, that's where the tree started off. And as you expand outwards from the middle of the tree rings, the first set of rings in the middle there are very wide or distantly spaced. And you can infer from that the tree had enough water and enough nutrients to grow throughout that year. So it was able to grow quite a bit. And it had favorable conditions. Whereas if you see on the outer edges of the tree ring, the rings become closer together, right, and much thinner. And those time periods you can anticipate being non-favorable conditions. So maybe there wasn't a lot of water, maybe it was a drought season, and maybe it didn't have a lot of nutrients. So instead of growing, that plant conserved its energy and put it elsewhere, right, instead of growing. Another way to determine past climate is by looking at seafloor sediments. And in seafloor sediments, you can see changes in the sediment composition. So you can see if there's a lot of calcium carbonate, so maybe there was a lot of productivity, or maybe you can see a lot of biology. And in that case, you can see that they were favorable conditions. Otherwise, if you just see a lot of byssal clays or ash maybe, then maybe it wasn't favorable conditions, all right? But again, you're not going to find of specific temperatures. You're just going to find generalizations. Another proxy data source would be bubbles trapped in ice. So you can see that ice core on the bottom right hand image there, and you can see the different layering that occurs within that that ice core there. And there's that really dark band in the ice, and you could probably infer that it may not have been favorable conditions when that time period was around, because usually something dark like that would indicate a lot of ash or a lot of dirt in the atmosphere, and so there was probably a huge eruption at that point in time, whereas the other parts of the ice core there that are clear and more white in color, those are areas where you have a lot of oxygen, probably favorable conditions. So definitely not a super warm period and not a super cold period. Next, you have fossilized pollen. So the top right-hand image there is that of fossilized pollen, and you can see there's all different shapes and sizes depending on the plant. But fossilized pollen can be used to see whether it was favorable conditions or not. Because if a plant is in rough conditions, doesn't have a lot of light, or doesn't have a lot of water or nutrients, it's not going to produce as much pollen as if it were in favorable conditions. So essentially in sediment or soil, if you see a huge quantity of fossilized pollen, then you know that then it was a favorable conditions. Coral reefs, you can actually cut them in half, much like a tree ring, and they actually show rings in their skeleton, so you can see like whether it was favorable conditions by looking at the rings in the coral as well too. Cave deposits, basically your guano, but essentially if it's favorable conditions, you can see large amounts of guano and other minerals that have precipitated into the cave, and because if it was not favorable, then you wouldn't see these deposits in the cave. And then also we've used historical documents. So a lot of the early explorers like Darwin and Sir Francis Drake and Edward Forbes and whatnot, all of those guys kept pretty detailed journals of climate conditions, maybe not to the degree, but definitely at least to a certain extent described whether it was cloudy or rainy, or the temperature was cool or warm, and such. So that's how we have determined previous climate conditions. And so the natural causes for climate change are these four things right here. Changes in solar energy, variations in the Earth's orbit, volcanic eruptions, and the movement of tectonic plates. So let's talk about each one separately. Solar variations, this particular one. And as we're going through each of these, I want you to keep in mind whether this is the cause of our current climate change, or if it's a combination of natural and human impacts that are causing our climate change today. But for solar variations, depending on changes in solar input, that could explain why we have periods of global warming. So when you look at this graph right here, you can see on the left hand side the total solar irradiance. And essentially what that means is how much solar radiation is being output. Okay, and then on the right hand y-axis there, you can see temperature change. So over time, looking at how much solar radiation is being received by the Earth versus the change in temperature, what you should take from this is, even though the temperature is rising right now, the amount of solar radiation is actually decreasing. All right, so if our solar radiation that's being received on Earth is decreasing, then why is our temperature still increasing? So in this case here, it doesn't make much sense that the amount of solar radiation that we're getting is the cause of our more recent climate change. So in the past, it may have been the case, but right now, currently speaking, it is not. So next would be the variations in Earth's orbit. And there are three main things that determine Earth's orbit: your eccentricity, the obliquity, and the precession. Now, the eccentricity is the shape of the orbit. So I have images of this on the next slide, but essentially the shape of the orbit, whether it's oval or round, will determine whether we have a warm or cold period. The obliquity is the angle of the Earth's axis that makes the plane of its orbit. So whether it's at an angle or whether it's straight up and down. And then the precession, so the wobble of the rotation of the axis. So think of like a top, like a spinning top. When you spin it, at first it spins really nicely and it stays pretty stable. But once it's right about to fall, it kind of does this like wobbly thing. That's what precession does to our Earth's rotational axis. Now, when these three variations in our orbit coincide, they amplify our climate conditions. So you'll see in a second, when they all get to the point where they are the closest to the sun, that's usually when we have really warm periods. And when they're furthest away from the sun, that's typically when we experience colder periods or ice ages. But not always. Okay, it's not always the case in that sense. But do keep in mind the time scales of these three variations of orbit are on very long terms. So let's go on to the next slide. It might make a little bit more sense. These three cycles, basically, are known as the Milankovitch cycles. It's named after a physicist. But here you can see the three different variations. You have your eccentricity, which is on a time scale of 100,000 years. So you can see the oval orbit of Earth around the sun will either expand or contract depending on whether it's close to the sun or whether it's furthest away. Your tilt would also be your obliquity, but essentially that's how much is the Earth tilted at. And so currently the Earth is tilted at 23.5 degrees, but it can range anywhere from 21.5 to 24.5, right? And this particular cycle takes 41,000 years to occur, right? So to go from 21.5 to 24.5, it takes 41,000 years. And lastly, you have your precession. So your precession is the wobble, and that will take anywhere from 19 to 24,000 years to occur. So now keep in mind, if you want to have an ice age, you have to have your eccentricity expanded out all the way. You have to have your tilt at the lowest tilt, so 24.5, and you have to have your precession pointing away from the sun. So that's typically when the climate on Earth will be the coldest. But looking at all of these timelines, that doesn't explain our current warming situation, because our current warming situation started, probably like 50 years ago, I would say. Let's see, where was that one timeline now? Here we go. So yeah, about 40 to 50 years ago is when warming really started to happen. So again, the differences in Earth's orbit can lead to climate change, but probably is not the source of our current climate change. Now, volcanic eruptions can change the climate because they'll have a cooling effect on Earth. So when a volcano erupts, it spews gases up into the atmosphere. Those gases reduce the solar radiation that hits the Earth and makes them bounce back into space. And back-to-back eruptions for extended periods of time have caused these climatic conditions to have a cooling effect on Earth. But it's a cooling effect. What we're looking for is a warming effect. So let's look at this next slide here. So you see this volcano is erupting and it spews up gases, and those gases block incoming radiation. So you have a temporary cooling of the surface. It does lead to a slight warming because you are trapping whatever heat that was already there. But overall, again, your effect will be a cooling. And so, for instance, when Mount St. Helens erupted back in 1980, the surrounding region experienced much cooler winters in the following years because of that eruption and because of all the material that was released up into the atmosphere. So again, volcanic eruptions is not the answer for our current climate change, but it could have been the reason for changes in climate in the past. And the last one is tectonic plate movement. So there is no current example of this today, but back eons ago, when the plates were shifting, it caused changes in ocean circulation. So a good example is the Drake's Passage. And before this Antarctica and South America, they were connected by that point right there. And when it got to a point where they continued to spread apart, it caused the currents in this particular area to basically go around Antarctica unimpeded. So before, the currents would not be able to go through the Drake's Passage and they would have to go around or find a different route. But because they were able to go around it unimpeded once those two continents broke apart, that was it. You were at that point, heat and moisture were able to be transported between the ocean and the atmosphere more readily. Okay, but again, this type of natural phenomenon occurs over spans of geological time. So this may not be the answer for our current climate change, but definitely at that time when this happened, this would have changed the climate drastically around the Antarctica and the southern tip of South America. So looking at this graph now, this graph would suggest that it is a combination of natural and human factors that contribute to our current climate change. So here you can see the global temperature change on the y-axis, and you can see the years on the x-axis, and you can see for a long time natural factors and human factors and the observations of climate conditions were pretty similar, right? But then once you get to about, let's just say 1965-ish, between 1965 and 1970, you start to see a divergence between natural factors and human factors. And you can see the purple shaded area that includes human factors with the natural factors, and you can see that mirrors our observations of climate change today, whereas the natural factors alone show it actually either decreasing or leveling off in terms of temperature change around the world. So there's your answer. So it's a combination, right? But primarily human impacts are causing climate change at this moment. Okay, so I've been showing you a couple of graphs about this lecture so far, but this graph right here is from your textbook, and what I want you to keep in mind is I've been showing you a lot of data, right, and some of it you can't really fathom, because, for instance, how do you fathom 100,000 years of the Earth's orbit changing, right? How do you see that? And so when you go, and if you want to do research on climate change right now, you're going to see a lot of graphs. But what I want you to keep in mind is, on this graph right here, what is this graph telling you precisely? Because you're going to, if you do some research in climate change, you're going to see a lot of graphs, but what are these graphs telling you? What is the message? What are they trying to convince you of? In this particular graph here, this graph is showing you the percentage of people who said yes, no, or I'm not sure to whether they believe climate change is a thing, right? And you can find this graph in your textbook, and you can see the dark blue color there is the general public. And generally speaking, when you ask them if climate change is a thing, the majority of them say yes, while there's still a good portion of them that say no, and there's still another portion of them that say, well, I don't know, right? And then you come to your climatologists. These are people who study the climate and the weather and whatnot. And you can see without a doubt that almost 88% of them believe, yeah, climate change is a thing. And then you have a smaller portion that say no, and then you have about an equal portion that say, well, I don't know, right? And then you have climatologists who are actively publishing research on climate change. And so that's the light blue color. And you can see that, what is that? 97% of them believe that climate change is a thing. And you have a smaller percentage that say no, and then another percentage that says, I don't know. Okay, so that's what this graph is telling you. But how is this data useful to you at all? What does this tell you about climate change? Yeah, all this graph is telling you is that there's a certain part of the population that says, yes, climate change is real and it's happening, and that's a good portion of the responses. But then you have another set of responses that are like, well, we don't know. I don't know if climate change is a thing. And then you have those that are like, no, climate change is not a thing. It's not happening. It's all made up, blah, blah, blah. Okay. So while this graph is great, the real message here is, how is this data useful to you? How has this data been doctored uh, to really say the message that the person who put it together wanted it to say? Because if you look at the people that they interviewed, you have the general public, okay, they may or may not know about climate change. Then you have non-publishers or non-climatologists. Then you have climatologists, and then you have active publishers. Then you have active publishers of climate change, and then you have climatologists who are actively doing research. So when you look at all of this, more than half of those categories right there are doing something with climate, right? Or know or have seen research about climate change. So in a sense, you're kind of skewing your data. You're forcing your data to say yes, climate change is a thing. Okay, and this is one of the negative things about science is you can pretty much make a graph about anything as long as you have data, right? So when you go out and you're looking at all of this research about climate change, be smart about it. Think about what the graph is telling you. How is this graph useful to you? How is this information been truthful or not truthful? So just think about it. Don't just rely on the first article that you come across and be like, oh my God, we have it all wrong, right? Just be smart about it. You guys are all in school. You guys are helping yourselves out. So when somebody like on the news throws a graph up and says, well, look at this now, stop and think about what they're really trying to tell you. And you'd be surprised about what you can find out when you do that. Next, we are going to talk about the IPCC, the Intergovernmental Panel on Climate Change. So this is a governmental organization that collects data on climate change from around the world, from all the scientists who are studying climate change at the moment. And the IPCC collects data over 4 years and then writes a report suggesting what is going on and what will be happening according to the data that is collected. So this particular graph is from 2014, but this year the new report came out, and fortunately it looks like we are still currently heading along the red track there. You can see the different colors in that graph. The red one looks like it goes up quite a bit, and then you have that grayish black looking one, then you have the yellow one, the green one, and the blue one. And what this graph basically tells you is over time, well, actually that's a gray color because the black is the historical and current data. And so back in 2014, our emissions rate was, I guess, about just under 40, was that gigatons of carbon dioxide per year, which is a lot. And I have to go and look to see what this year's one is. I haven't had a chance to read the report, but I do know that it's not looking very good. But what you can tell from this chart here is that everything that's in red are scenarios. Well, pretty much all of these lines that are on this graph are scenarios. And these scenarios try to predict what possible sources of CO2 would be, and try to predict whether things will remain the same and not change, like the red one is. So the red one is business as usual, is what it's known as. And essentially, we don't make any changes to our way of life. We don't recycle. We don't stop burning fossil fuels. We don't look for alternative clean clean energy ways. So that's what those red lines represent, is just different scenarios of the business as usual model where we don't change anything. But if in contrast, you can see the blue model. So the blue model is suggesting that if we cut out all burning of fossil fuel, we replant, do reforestation, we find cleaner alternative energies, and recycle, and do all the things that maybe we should be doing, right? Depending on how you feel. If we did that, this model shows that over time, the amount of CO2 in the atmosphere will decrease to the point where it goes below what they call the net negative global emissions. So it would go below that point, which typically speaking, as you can see in our more recent past, since the 1980s, that hasn't been the case. But there have been times in past where it has gone below that zero mark. But they try to look to see how human effects will change climate change and global warming. And they publish those assessment reports every 4 years. So this year report came out, and then in another 4 years, another one will come out. All right, so on this slide here, they're written every 4 years, and in the 2014 assessment report, they predicted that a 1 degree to 3.5 degrees Celsius increase in temperature would occur, right? I believe, I didn't get a chance to read it though, but I believe I remember hearing somebody telling me that it actually jumped up to about 3.5 to 4 degrees Celsius now. So it's the predicted temperature increases is increasing. And so just like this graphic shows you, are we all going to die? Because I'm talking about 1 degree Celsius. As humans, we're not going to die. At least I hope we don't, from a 1 degree change. But you have to stop to think about the microscopic organisms in the ocean. A 1 degree change every year can be very significant. All right, the temperature changes in the ocean are not just purely 1 degree, like we wouldn't even flinch at 1 degree, or even 3.5 degrees. It wouldn't matter to us. But you have to think in terms of the coral polyps. For them, a 1 degree temperature is more like 10 times that amount. So think about a 10 degree temperature change instead. Then we're talking, right? So let's just say, here in Hawaii, our average temperature is about 80, let's just say 80 degrees, all right? Which is, actually, I think the average temperature is a little bit higher than that, but for example purposes, so let's just say the average temperature here in Hawaii is 80. But if we do a 10 degree change, right, and say let's increase the temperature by 10 degrees, well, now it's at 90 degrees. That's getting kind of warm. Yeah, I mean, I don't know about you guys, but I don't care for the heat whatsoever. So a 10 degree change for me would really stress me out. And so that's kind of how these corals feel when they go through a 1 degree change. It's equating it to like a 10 degree change for us, right? So are we all going to die? Probably not, but we're definitely going to get stressed out. The coral reefs in particular are going to get really stressed out. So are we all doomed? Humans may not feel the effects, but other species will, like I was explaining in the last slide. And corals are highly sensitive to temperature changes, so even that 1 degree increase that was projected in the 2014 assessment report is a really big deal. And now that the 2018 report is suggesting 3.5 degree increase at the minimum, that's going to be pretty severe for the corals. So it sounds like it's all doom and gloom. It sounds like we're going to lose all the corals, but in reality, a lot of corals will die, but some of them will survive, and the ones that survive will make the species stronger. Just like everything else in life. Those species that can adapt to the rise in temperature will have a better chance. There have been some studies suggesting that certain zooxanthellae species are more heat resistant than others. So if a coral can incorporate that more heat resistant zooxanthellae into their tissues, then they will be better off. So what contributes to climate change and global warming? The first thing you need to understand is the greenhouse effect, because what's going on is the heat is getting trapped within our atmosphere and it's not being allowed to escape. And because it's being trapped, it's just continuously heating up our Earth. And this example of a greenhouse is a perfect example, because what it's meant to do is to trap heat so the plants within the greenhouse can survive during the winter time. So short waves from the sun, short wavelengths of radiation enter the greenhouse. When it bounces off of the greenhouse floor, they are converted into long wave energy, and that long wave can escape, but some of the short waves that are coming off of the ground cannot escape the greenhouse. So they stay within the greenhouse and continue to heat it up. Our atmosphere, with all of the pollution in it and whatnot, acts as a greenhouse for the Earth. So it is trapping all of that heat that comes in, and that heat just keeps bouncing around in between the Earth's surface and the atmosphere and continuously heats up the Earth's surface. So certain gases, which we'll talk about in a little bit, act as a greenhouse and trap that heat within the troposphere. So these greenhouse gases are these 5 right here: water vapor, carbon dioxide, nitrous oxide, ozone, and chlorofluorocarbons, or CFCs. I'm not going to talk about water vapor, because water vapor, while it is a greenhouse gas, it also is a natural gas that's supposed to be in the atmosphere. Even though, not to say that the other ones are not natural, but they are a more prevalent problem than water vapor. All right, so carbon dioxide is the largest contributor to the greenhouse effect. When carbon dioxide is released, it is colorless and it is odorless, so you can't smell it. When you smell the exhaust from your car, you're not actually smelling carbon dioxide, you're smelling other things like sulfur and some other stuff I can't remember now, but nasty stuff basically. Carbon dioxide is released when you burn fossil fuels or you respire. So by you just breathing there, you're releasing carbon dioxide into the atmosphere. So we're all contributing to the carbon dioxide in the atmosphere, which is normal. I mean, majority of us drive to work or drive to school, so we are all responsible. Even I'm responsible because I drive. But and I breathe too. I hope I'm breathing. CO2 has increased by 40% over the past 250 years. So that's a pretty significant amount to increase in the atmosphere. And about 73 billion pounds of CO2 is released into the atmosphere every year. So that is a ton of gases going into the atmosphere. Now, if we look on this slide here, this is the amount of carbon dioxide in the atmosphere over time. And you can see starting from about 1955 all the way to 2015, you can see the concentration of CO2 steadily increasing to, it's probably over 400 at this point. But this is known as the Keeling curve because this instrument was put at the top of Mauna Loa, one of the volcanoes on the Big Island. And the reason why they put it at the top of a volcano in the middle of the ocean is because what they are looking at is the overall CO2 concentration in the atmosphere. They wanted a pure sample, one that wasn't affected by daily, everyday activities. So, for instance, if they put it down at HCC, they might get a higher concentration because of all the traffic that goes by, all of the industries that are nearby. So they wouldn't get an accurate measurement of what's actually in the atmosphere. And by putting it on top of a very tall mountain in the middle of the ocean, they can get a pretty good idea of what the actual concentration is in the upper atmosphere. That's not tainted by everyday activities. So the next type of greenhouse gas is methane. Methane is the second most abundant greenhouse gas in the atmosphere, but per molecule methane has a greater warming ability than CO2. So even though there's a ton of CO2 in the atmosphere, if you compared one molecule of CO2 to one molecule of methane, one molecule of methane would be able to warm up or trap more heat than that one molecule of CO2 would. So methane can and is a problem. Methane is generally released into the atmosphere by landfills, so that degradation of that trash releases methane. Cattle are notorious for farting and releasing tons of methane, and agriculture. So when you process the food that you grow, it releases methane. So if you look at this image here, it compares the emissions of animals or humans and how much methane they produce every year per individual. So for instance, a Western cattle, which is they make a distinction between Western cattle and non-Western cattle, because Western cattle, like the cows that we have here in America, are fed highly processed grains with a lot of antibiotics in it. And so when they eat that grain, it tends to produce more methane than cows that don't get fed that same feed and just eat naturally, like grass and whatnot. So as you can see in this graph, that Western cattle will produce 120 kilograms of methane per individual per year. Okay, so that's quite a bit. And then when you look at your humans only produce 0.12 kilograms of methane per individual per year. So far less, right? But I had a student who was very curious to see exactly what the numbers came out to be when you accounted for all the humans and all the cows, because even though the cows are 100 times more, like they produce more methane by 100 times than humans do, humans have a greater population. So when you do the calculation and you multiply the amount of methane each human produces by our population, which is about 8 billion, probably verging on 9 billion at this point, when you calculate that number, it outweighs the number of cows around the world producing 120 kilograms of methane by quite a bit. I don't know what the numbers are, but essentially, if you want to try this thought experiment, feel free to. There were about 1 billion cows worldwide that produce 120 kilograms of methane versus 8 billion humans that only produce 0.12 kilograms. So, needless to say, humans are producing quite a bit. Some other gases to keep in mind are the nitrous oxide, ozone, and CFCs. These ones will absorb more infrared radiation, so the radiation that's coming in, that it will absorb that and actually trap that heat and keep on heating the world, the Earth's surface. But they are smaller contributors to the greenhouse effect, so they're not a huge problem unless you're in places like LA, which is this image right here, and during certain times, the ozone around downtown LA can get really bad. So that kind of brownish fog-like material surrounding the downtown area, that is ozone that should be in the upper atmosphere but is down by the surface. And when that happens, it causes tons of respiratory problems. It can cause cancer, a whole slew of health problems can occur. So while it does a really good job at protecting us from any unnecessary radiation that comes down from the sun, when ozone is found near the surface, it can cause a lot of problems. So let's see, this graph right here shows you what CO2 concentrations were like before modern day. So on the right hand side of this graph, where the 0 is in terms of age, that's modern time, and then this is looking at, say, 800 or 1,000 years before the present. So it's looking at time past, the past 1,000 years, and it's looking to see what the CO2 concentration was and what the methane concentration was. And as you can see, the top blue line is your CO2 concentration. And while it doesn't really look like there's any real pattern to it, it just looks like it goes up and down depending on what's going on. You can see that there are times where the CO2 concentration is higher and there are times when it's lower, right? And then there are times in the past where methane has been higher and methane has been lower, and they seem to coincide with each other. So when you see times of high CO2, you also see times of high methane. And the middle line, the black line, is your temperature anomaly. So it's looking at the difference in temperature over time, and you can see there's periods of warming and periods of cooling. So when you have periods of cooling, that's generally when you see a low concentration of CO2 and methane in the atmosphere. When you see the temperature being higher, that's when you see a lot of CO2 in the atmosphere and a lot of methane in the atmosphere. Okay, but one thing to keep in mind is at present day, we're off the chart on this graph right here in terms of the amount of methane and the amount of carbon dioxide that we have in our atmosphere. So yeah. Some other considerations to take into account are aerosols. Aerosols are suspended particles in the air, so the image on the right hand side there of that black smoke coming out of that tower, industrial tower right there, is full of soot, and that soot is actually a particle that is suspended in the air, and it's a big contributor to global warming. It does have a chance of creating clouds, and when you create clouds, you inhibit warming, but it can also inhibit clouds. So there's an equal chance of creating and inhibiting clouds. But this black stuff right here lowers the albedo of Earth, because all of that soot will then fall into the Earth. And instead of that solar radiation bouncing off of the ice and going back into space, it gets absorbed by the ice and melts the ice. So that little critter right there is my little cartoon version of the black soot that's coming out of that tower. If any of you are familiar with Miyazaki's films, then you'll know where that little soot came from. Okay, so here are just some documented changes from climate change. So over the past 30 years, the average sea surface temperature has risen by 1 degree Fahrenheit. So again, while that's not too bad for us, it can affect corals and other organisms quite a bit. The rate of warming has doubled in the past 50 years, so that's compared to other times. And the top 10 warmest years have all occurred within 2000. So in this decade, between 2000 and 2010, that was the warmest decade. Although I think maybe between 2010 and the decade that we're in right now might be the warmer one. But 2014 was the warmest year of all, although I think maybe 2016 might have beat it. It was pretty warm. This has been the largest increase in sea surface temperature in the last 1,300 years. So in the last 1,300 years, we have not seen such a drastic increase in surface temperature. Sea surface temperature has risen as well too, as well as the amount of heat waves. So whenever you have intense periods of heat, that's what I'm talking about. So let's see, how does this compare to other models? All right, so this is a very similar chart to what I showed you earlier, but the main point is we are currently following the red line, which is your business as usual model. The yellow line is the one where we stop doing all the things that we're doing and try to recycle more and use cleaner energy and whatnot. And the blue and green line are scenarios that take into account some sort of change in our habits, but not completely. So you can see the blue one, we've changed a little bit more, but not a whole lot. And the green one, maybe we only did one change, or let's just say we just did recycling and nothing else. We still burn fossil fuels. We still don't do a whole lot of sustainable agriculture and whatnot. So just keep that in mind. But what the models don't take into account are the reactions from feedback loops. So when we talked about the sun coming down, heating up the surface of the ocean, creating more water vapor, and that water vapor getting up into the atmosphere. And sometimes that water vapor will then create clouds. Well, when it creates clouds, then that creates a cooling effect on the land. And so those models can't account for all the instances in which clouds are formed because the sun comes down and creates water vapor. So that's the only drawback from these models. It's just assuming that however many clouds are present in the sky, there's not going to be any more than that. But what the models do agree upon is that there will be earlier summer seasons with higher temperatures, and there will be more extreme precipitation events. There will be a retreat in ice worldwide, most likely to the point where you don't have any ice whatsoever. You can get water contamination that leads to disease outbreaks because unlike first world countries where we filter our water, a lot of places do not. And so when you increase the temperature, you increase the likelihood of diseases and contamination occurring within freshwater bodies. And you'll see a shift in plant and animal community ecosystems. So, for instance, let's see, what's a good example? Well, on the Big Island, there were these birds, which I call francolins. They're called francolins, and they're these small little quail-like birds, and they like the warmer temperatures. So typically, you wouldn't see them in my hometown in Waimea when I was growing up. But because the temperature has increased in my hometown quite significantly, I might add, you can now find them in my hometown. So when I was a kid, average temperature would range anywhere between 60 and 70 degrees, even during the summertime. And that was too cold for these francolin birds. But now during the summertime, it regularly gets up into the 80s. And so these francolin birds have been migrating up from the beach up to where my hometown is in the mountains because the temperatures have started warming up. So that's what I'm talking about when I say shifts in plant and animal community. You will see animals moving to a different area where it's more comfortable for them. Okay, but there may be an upside to all this, right? So far it's all just been doom and gloom and everything's going to die, the temperature is going to get so hot, nothing's going to be able to survive. But the models do suggest that the longer summer will mean that there will be a longer growing season for crops. So instead of just 3 months during the summertime where you can grow whatever vegetables you need, maybe it'll increase to 4 months. Maybe that extra month will be good because then we can produce more food. The increase in carbon dioxide will also lead to an increase in biological productivity. So in the ocean, the plankton can take advantage of that CO2, and that can help them grow. And technically speaking, if you have an ice-free Arctic, you can have a very highly productive area up there as well too. But again, you're taking away a habitat up there from different organisms. So it's a catch-22 on that one. But again, this is all regional because some areas will tend to heat up more and turn into more of a drought-like area. And then you'll have other places that have increase of precipitation. So it'll be even more rainy than normal. But how does climate change affect the ocean? Well, climate change increases the ocean temperatures. It increases the surface temperatures, which when you increase the surface temperatures, you are leading to more hurricane events. So hurricanes rely heavily on the warm surface waters, and when you increase those surface water temperatures, you're increasing the amount of hurricanes that can occur. You'll see changes in deep ocean circulation, so that ocean conveyor belt that we talked about, that will change. You'll get melting of polar ice. You'll get increased ocean acidity, so the corals won't like that. You'll also get rising sea level because you're melting all of the polar ice. And I'm sure there's other changes that I don't know about. Let's see. Increasing temperatures. So increasing of temperatures in the ocean is not uniform. Temperatures will increase at the surface water quicker than it will at the deep, and temperatures will increase quicker near the equator versus the polar regions. But if you look at the change in, or the temperature anomaly, so the change in temperature is greater in the polar regions because you go from really cold temperatures to warm temperatures, versus at the equator, it's always warm. So there's not a great change in that temperature. But the greatest temperature changes, there we go, will be at the polar regions and then the deep ocean. Positive feedback loops for melting ice caps will increase because of the warming oceans. So you're going to continue to increase melting of those ice caps because warming is going to continue to happen. Alright, so this slide here, you can see between 1901 and 2015, you can see the change in sea surface temperature, and you can see that over time it has greatly increased to the point where some places have increased as much as 3.5 degrees. I'm sure by now it's increased by more, but there's one spot in particular that has not increased, and that's near Greenland, which I want you to think about why that one has not increased but actually decreased. So we'll come back to that one in a sec. But if we look at this slide right here, you can see in 2014 there was a significant amount of coral bleaching that occurred in Hawaii, the Marshall Islands, and Guam, and the Marianas Islands. And in 2015, I should say, 1 year later, a massive bleaching event occurred all around the Pacific. And then in 2016, you can see that bleaching occurred in the Indian Ocean as well as the South Pacific. So it has been a serious problem, and we've had a number of bleaching events here in Hawaii as well too. The increase in sea surface temperature will increase the amount of hurricanes that occur. So every year, if you've noticed, we've had an increased number of hurricanes that occur. Thankfully, none of them have hit Hawaii, but we have had some pretty close calls. And the additional evaporation of the sea surface water that turns into water vapor is what fuels the hurricanes. So you'll over time you'll start to see larger hurricanes occurring, which is what's happening in the Atlantic Ocean right now, when all of those hurricanes that have been hitting like Florida and Louisiana and whatnot, those are some pretty large hurricanes, and they can create a lot of damage. Okay, so now let's come back to that question. Why is there a blue patch near Greenland? And what's happening is Greenland is covered in ice, right? I mean, you guys all know the story about why it was called Greenland, right? It was called Greenland because the Vikings who found Iceland didn't want to let other people know that Iceland was such a good place to live at. So they called Iceland ice so that people would avoid it. And they called Greenland Greenland because they wanted people to go to over there where it was uninhabitable and full of ice and undesirable. But because of all that ice that's on Greenland, that is now melting, all of that melted water needs to go somewhere, and it goes into the ocean. So that blue patch right there is just all of the melted ice that has now turned into liquid water and is going to the ocean, and it's cooling the ocean in that particular area. But the thing that's special about that area, if you remember from the Currents chapter, which I think was chapter 7, that's a spot where deep water forms, right? That begins your deep ocean circulation, right? So if all of that cold, fresh water is entering a spot where you need very salty, very cold water to occur, you're going to effectively shut down or slow down that ocean conveyor belt to the point where maybe it might stop completely and you won't have any deep ocean circulation, which could potentially affect a lot of the organisms at the deep because they rely on the downwelling over there to bring oxygen down. So here, this is just an example of how deep water forms. So you have warm water from the equator that comes up. It enters the surface waters near the polar regions where where fresh water is extracted and sea ice is formed. So what's left behind is super salty and super cold water, which then sinks and turns into your Antarctic bottom water, and it flows back towards the equator, right? But when that water sinks, it picks up oxygen and it takes it with it. So it's essentially oxygenating the deep ocean. But ice caps melting they're melting at an alarming rate, and to date we've lost about 800,000 square miles of ice worldwide, right? So you can see on these images right here, there's actually guys standing on this glacier on the image on the left hand side, and look at that flow of water coming off of that glacier. Okay, that's a giant amount of water that is constantly flowing off of this glacier. Now keep in mind, liquid water is the most stable form of water. So when you have a river of water like that, you will continue to erode the ice and convert everything back into liquid water at that point. And here you can see whole pieces of that glacier falling off into the water. So here's an aerial view of ice melting on Greenland, and you can see in 1992, which is on the left hand side, all the orange spaces are areas where active melting was occurring. So it was a pretty decent amount, but not a whole lot compared to 2002, where that it looks like the amount of ice on that glacier that's melting doubled in size or even tripled, depending on how much area you're talking about. So a lot of that glacier is now melting. Here's another example in Antarctica. I don't remember exactly what this ice shelf was called, but you can see the blue dotted line. Everything to the right of the blue dotted line was there prior to 1993, and in 1993, the part that was to the right, or the part of the ice shelf that was to the right of the blue dotted line, fell off, broke off into the ocean, and no longer existed. Then in January of 2002, everything to the right of the red dotted line broke off and went into the ocean. And then in March, so 3 months later, everything on that ice shelf broke off and melted into the ocean. So this ice shelf no longer exists now. But when you increase sea surface temperatures and atmospheric temperatures, you are destroying habitats for these critters right here, who rely heavily on sea ice and glaciers to make to survive. Right? They rely on it not only for food resources but for habitat um, and for survival. So if we don't do something about it, who knows? Maybe these organisms will only be found in zoos at some point in time. And when you increase the ocean acidity, you are decreasing the ocean's pH, okay? Which means you're making it more acidic. And half of the CO2 released into the atmosphere stays in the atmosphere. A third of that CO2 that is released up there goes into the ocean. Okay, so that's a pretty significant amount. And when it goes into the ocean, it acts like an acid, which then acidifies the ocean. And when you acidify the ocean, you can cause changes in biology. So, for instance, this image right here is that of plankton that creates a calcium carbonate shell. And that shell, when you put it into slightly acidic conditions, you can see that shell starts to change, becomes more opaque until it finally starts to deform, until you finally get to a point where it's almost non-existent. So that's essentially what's going to happen to a lot of the coral reefs and a lot of the organisms that rely on calcium carbonate. The other point to raise is that when you melt all of the sea ice and the glaciers, you'll inevitably raise the sea levels. And because of that, you'll raise the sea levels around the world, and partially due to thermal expansion of water. So when you heat up the water, you can expand it, but also you're introducing back all of that fresh water into the ocean when you melt the ice caps and the glaciers. And so typically these sea level rises will affect coastal regions and islands. So here's a graphic of Waikiki, and as you can see, majority of Waikiki is underwater by at least 3 feet, and I think nowadays they're predicting greater than 3 feet rise. I think it's closer to 4 or 5 feet now. But you can see majority of the LOI golf course is underwater. Majority of the hotels are underwater. Magic Island is actually an island now. And the LOI boat harbor is it's a floating harbor now, right? Okay, so some of the predicted and observed changes are you'll see changes in dissolved oxygen in seawater. So because the water will be warmer, you'll have less dissolved oxygen in the seawater. You'll see an increase in wave speeds and wave heights. You'll see migration of mangroves. So mangroves like warmer temperatures. So you'll see them expand into areas that they previously were not in. You'll see potentially an increase in ocean productivity by the increase in CO2, and it can have an effect on marine organisms like corals. So the dissolved oxygen will, the ability for seawater to hold oxygen will decrease, right? Because you're increasing that temperature. And because of this, you'll cause higher metabolic rates to occur within organisms. And as you can see, the water column is stratified. Stratified. So as you go deeper, you have less oxygen, and it's colder. So, the colder water can hold more oxygen, but typically you don't have as much oxygen in the deep because it doesn't have access to the ocean surface. And when you increase wave speeds and wave heights, it'll lead to higher waves. So here are just some images of different wave heights. So as you can see, the 1 foot and 2 foot are not too bad, but once you start getting into the 5, 6 feet, 8 feet plus waves, those can get pretty devastating, especially along the coastal regions. And your mangrove migrations, those will expand into areas that they were not seen before. Normally, the colder water temperatures will keep the mangroves out, but if we continue to increase the water temperature, they will expand as high as North Carolina, which normally you shouldn't see mangroves in North Carolina. Ocean productivity will increase, and as you can see here, you'll see a decrease in upwelling and nutrients brought up to the surface, because you'll effectively will cut off your ocean circulation, your deep ocean circulation. So while you may have an increase in productivity due to an increase in CO2 at the surface, those upwelling areas will decrease because you're no longer bringing stuff up from the deep. And then the effect on marine organisms that it has is it will affect the food supply. So you may or may not have enough food to survive. You'll lose habitat, like this polar bear. This polar bear is losing its icy habitat, and it will force other organisms to migrate into a habitat that's more suitable for them. So what can we do? As usual, you can reduce, reuse, recycle, or you can carpool or take public transport. That's one way of reducing your greenhouse gases. They have tried to do things like introducing large amounts of iron into the ocean, and the iron causes a sudden increase in productivity, which then causes a drawdown of carbon dioxide from the atmosphere, and then effectively traps that carbon dioxide in the deep ocean. So scientists have been trying to find ways around, but in reality, the main message should be we should all do our part in trying to lessen our carbon footprint by either carpooling or taking public transportation, or even biking or walking, or just recycling and not using as much as we need to. Anyways, that was chapter 16. So that is it for lecture material. Stay tuned for information about the third exam, which will be given during finals week.